In this example problem, we are going to have a spring. We're going to use a block to compress that spring by a distance of, no, that's not where I want to put that. We're going to compress the block. We're going to use the block to compress the spring by a distance of 35.0 centimeters. So that's a little hard to read, but that's 35.0 centimeters. We're going to compress the spring using the block 35 centimeters. The block is then going to be released from the spring because we're going to let go. The spring is going to push the block over here, and then the block is going to slide along this surface, this level surface, until it comes to an incline, and it's going to slide up the incline. So it's going to come over here and then slide up the incline until it gets to some final height up here. Some piece of information that we know: the spring constant of the spring is 560.0 newtons per meter. The mass of the block is just 2.00 kilograms. The angle of the incline is 25.0 degrees. The level surface has a coefficient of friction equal to 0. So there is 0 friction on the level surface. However, the incline itself does have a coefficient of kinetic friction, which is equal to 0.260, and that's on the incline only. We are looking for two things in this problem. We're looking for the maximum height to which the block is going to rise. We're also looking for the work done by the force of gravity on the block during this whole event. And yes, you can clearly see that I made this problem up myself.
With the coefficient of friction being 0, is
yes.
It's kinetic, right?
It doesn't really matter. It's just there's no friction on this surface
here.
Okay. So on the level surface, there's no friction. Let's see. Let's start with the work done by the force of gravity. The first thing you need to identify about the work done by the force of gravity is that we actually have to do it in two parts. We have to do the work done by the surface, work done by the force of gravity on the level surface. And we also have to figure out the work done by the force of gravity on the incline. Why do we have to separate the work done by the force of gravity on the level surface from the work done by the force of gravity on the incline? Figure those out separately. Leah.
On the level surface, it's just 9.8, but then for the incline, you have to separate the perpendicular and parallel.
Well, there are a couple issues I have with what you said. First of all, you said that the force of gravity is 9.8. What's 9.8 meters per second squared? It's the acceleration due to gravity. Okay, good. They often get confused, right? The force of gravity and the acceleration due to gravity. On the incline, I agree it has to do with the parallel and perpendicular, but I need more specifics on that. So let's just give me a second. Let's write out the equations here. So clearly we're not quite seeing it. That's okay. We have, this is going to be the force of gravity times the displacement times the cosine of theta. This is also going to be the force of gravity times displacement times the cosine of theta. Class, what's the equation for the force of gravity? Okay, that didn't work very well. Let's try that again. Class, what's the equation for the force of gravity?
M times G.
M times G, mass times the acceleration due to gravity. So we have mg times d times the cosine of theta. On the level surface, class, please point in the direction of the force of gravity. Should be pointing down. Please point in the direction of the displacement on the level surface. What's the angle between down and to the right? 90. Cosine of 90, class? 0. So we've just shown that the work done by the force of gravity on the level surface is 0. Is that angle still 90 degrees when it's on the incline, class?
No.
No. So notice that's why we need to figure out the work done by the force of gravity on the level surface and the incline separately. So now we need to figure out what the angle is on this incline. We have mass times the acceleration due to gravity. The displacement, I'm going to put, that's going to be the delta d parallel, the displacement in the parallel direction. We've already worked with that variable. And this is times the cosine of, and we need to figure out the angle. So let's draw a picture here so that we can figure out what this angle is. We have the incline. We have the object on the incline. The force of gravity is straight down. This, and let's do this, extend this a little bit. The force of gravity is straight down. We know this angle right here is 25 degrees. Class, we know the force of gravity is straight down. Please point in the direction of the displacement of the object while it's on the incline. Point. Up the incline, right? So we need the angle between the force of gravity and the displacement, which is this angle right here. Nick.
Wouldn't it be 90 plus 25?
It ends up being 90 plus 25. Let's work our way through that to make sure we understand where that comes from. It ends up being 90 plus 25. If you look, this is 25 degrees, this is 90 degrees, that makes this 65 degrees. That makes this angle right here 25 degrees. Just like, and we already went through this, where we know this angle right here is the same as the incline angle plus the 90-degree angle or the right angle, which is right there. So in our work due to the force of gravity on the incline, the angle is the 90 plus 25 or 115 degrees. We have the mass of the object. We have the acceleration due to gravity. We do not have the displacement in the parallel direction. So in order to finish figuring out the work done by the force of gravity, we need the displacement in the parallel direction. So let's return back to the problem. Leah, what did you bring up that we were not adding to the table of friends? Conservation of energy. Who can tell me when energy is conserved? Conservation of energy. Wicked.
There's no friction.
When there's no friction. So we are going to use this equation. Mechanical energy initial equals mechanical energy final. Conservation of energy. Whenever we use this equation, we need to identify some things. Who can tell me what we need to identify whenever we're using conservation of mechanical energy? Not Heather, he loves to drive the bus. I need other bus drivers. Other people to decide where we're going to go. Things we need to identify whenever we use the mechanical energy initial equals mechanical energy final equation. Now, yeah, I understand. You're a bus driver. Come.
We have to add all the initial mechanical energy.
I agree with that. That's not quite what I'm going for, but we'll get there. We have to add up all the energies, right? We have our kinetic energy initial. We have our gravitational potential energy initial. We have our elastic potential energy initial, our kinetic energy final, our gravitational potential energy final, and our elastic potential energy final. Therefore, we get 1/2 mass times velocity initial squared plus mgh initial plus 1/2 kx initial squared equals 1/2 mv final squared plus mgh final plus 1/2 kx final squared. Right. I agree with that. But we can't do the next step. What should the next step be? Sam?
Should we identify our variables?
Identify, but what do you mean by identify variables? We're close.
Like height final and then 0.
Right, but we can't even talk about height final yet. Because we have to identify certain things. Brian?
Like which of like the equations that we use?
Which ones are going to cancel out, right? We can't even do that yet because we have yet to do what we need to do first before we can use this equation. Andy?
Well, there's friction on the incline, so maybe you can only do the mass or the mechanical energy for the place where there's no friction.
I agree with this. He just identified that there's friction on the incline. Conservation of energy is only true where there's no friction, so we can only use this on the level surface. True. But we still have yet to identify those things we need to identify before we can use this equation. Before we can start crossing off, for example, if we could cross it off elastic potential energy initial, for example. I'm waiting, because this is review. If it's not in your brain, find it in your notes. Whenever we use this equation, I can't visually see some piece of very critical information. Kraus.
You have to find the zero line.
One thing we have to do is identify our zero line. True. What is a good location for our zero line? Connie, we'll get there in a minute. What's a good location for the zero line? Josh. Say again? Right where it is in the picture right here. We can identify this as our zero line, our horizontal zero line. What is the other thing we need to identify before we use this equation? It's a good spot for a zero line. Connie?
It's like the final and the initial.
We have to identify where the object is initially and where it is finally. So what is our initial point? Knickerbocker?
When it's at rest on the spring.
Right here, this is our initial point. What is our final point? Mitch?
At the top of the incline when it stops.
Which is one of the reasons we have to identify our initial and final points. Who can explain to me why this cannot be our final point? Sorry, Mitch. This cannot be our final point. Brian?
The work done by the force of gravity is different in the two.
Yeah, but actually this is something that's entirely separate from what we're doing right here. So that doesn't have to do with why this cannot be our final point. Mitch?
Is it right before it goes on the incline because that's when friction's still zero?
Because this equation is only true when there's no friction. When we get to the incline, there is friction, so we can't have, mechanical energy is no longer conserved. So the final point actually has to be right here, right before the block hits the incline. So this has to be our initial and our final points. One moment, please, just a second. So please, whenever you're going to use the conservation of mechanical energy, you have to first identify your initial and your final points and your zero line. Then you can move on. Ellen.
Isn't there still friction on the horizontal, or are we just pretending there's none?
Pretending, such an interesting word. There is no friction on the horizontal surface.
Why?
Because that's what I decided. This was my problem. I said there's no friction on the horizontal surface.
Oh, I see.
If you make the problem,
I
you can
see
make
it.
other decisions. Go, son.
So we know the work on the horizontal surface is zero.
True.
So why are we even doing anything with the horizontal surface anymore? Why do we have the initial and final point there? Can't we put why are we even using that equation?
It's a fair question.
I don't know.
Okay. I don't know either, clearly. What would we do instead? Okay, in the absence of nothing else to do, should we do this?
I mean, yeah, but I'm just.
How about we'll come back to your question?
Yeah.
Because it's a fair question, but at this point, we don't quite have the vision to be able to see exactly why we have to do this, and that's true sometimes, right? Sometimes in this class, we start something, only because I don't know what else I would do at this point, and then you figure out why you're going to use it in a little bit. Headley.
Do we not need to find some additional information before we can work on the other part of the problem?
What's the other part of the problem?
Being the incline.
On the incline. There's more information. There's information we need in order to solve the incline. We don't have enough information yet. And you'll see what we're going to find from doing this. Okay? Nick.
So we're basically solving for the velocity here
So what we're solving for is the velocity where?
on the flat surface.
Right here. So that we can figure out the velocity going up the incline, then we can solve the incline. So that's where we're headed, is we're solving for this final velocity. So now, looking at our giant equation, things we can cross off. I'll take volunteers. What can we cross off and why? Josh.
Height initial is zero.
Height initial is zero, therefore the gravitational potential energy initial is zero. More. Mitch.
We can cross out the first kinetic energy inertial because velocity is zero.
The initial velocity is zero. We push the block onto the spring and then we release it, so the initial velocity is zero. More stuff we can cross off. Nick.
Height final is zero.
Height final is zero as well, therefore we can get rid of the gravitational potential energy final. There is one more.
There's no spring at the end, so you can
At the end, the mass is no longer attached to the spring, so it's not on the spring, so we can cancel off the elastic potential energy final. So what we end up with here is 1/2 kx initial squared equals 1/2 mv final squared. We can multiply both sides by 2. We get kx initial squared equals mv final squared. Solving for v final, we get that velocity final equals kx initial squared divided by the mass, the square root of. So we get for the velocity final. Please give me all the numbers here. Stecker, what is the spring constant?
560.
Good, multiplied by x initial. 35 centimeters,
Okay.
which I'm going to square divided by the mass.
2.
2 the square root of.
5/8.
Nick?
The spring is 35 centimeters, should that be in meters?
Should we use meters for the displacement from the equilibrium position?
Yes.
How do we know we need to use meters, Meredith? The spring constant is in newtons per meter, so we need to match that. So we need to use 0.35 for the meters for the position here, or the displacement from equilibrium position dash.
Does that have to be negative?
It doesn't really matter whether it's negative or not. I suppose in this particular case it probably should because it's to the left, but we end up squaring it. So, negative. All right. So we get, what's our final velocity here?
5.856
Great. Just to make sure we understand, remind me where, Lily, specifically is this final velocity?
Right before it goes up.
So this is at the base of the incline.